So in a couple of slides, I'm trying to show you what are the main differences between the Quest algorithm and the extended common filter. I already prepared the one of the Quest algorithm because it is something that we have seen in depth, so you don't need to go in further details. But it is in this schema enables to have a better understanding. So what I mean with this blue dot here is that let's start to have, so before the time t0, we have sensors, for example, star sensors that are in the operation mode called star tracking. So we already identified the stars, and we're trying to use the sensor to determine the attitude at that initial state. For the Quest algorithm, we have seen that the problem is only eigenvalue, eigenvector problem. So we have to solve this equation by using the characteristic equation for the Quest algorithm. And we are going to determine the quaternion Q. I wrote here that the quaternion Q is going to also call the P0, where P0 will only be the vector part of the quaternion. Okay, so P0 will be equal to this quaternion Q computed at the time T0 with the Quest algorithm. The Quest algorithm also enables the estimation of the covariance matrix by using this approach with the theoretical assumption that we have seen before. So what we are going to do here is that at that time, we're going to have an estimation of P0, and we are going also to have the covariance matrix.
Ricordatevi, mentre ti sto dicendo che quando lei mi fa scena.
So please mute your microphone, because otherwise I have to mute for you. Also because now, oh, okay. So the initial state give you the quaternion at P0, at time T0 called the P0. So this is the vectorial part of the quaternion. This is the covariance matrix at that time. After a certain time, let's say 1 Hz, so every second, we have an additional measurement of the star tracker. So we are not going to use the previous information, but we are going to do the same approach that we've done before. So we are going to remeasure the quaternion, assuming that P1 is equal to the vectorial part, and we're going to determine the covariance matrix. So there is no relationship between the two states. What we are going to do with the extended common filter, that's the reason why I like to clarify some of the demonstration that we have done before. So the nomenclature that we're going to see is indeed the P0 is the estimation of the vectorial part of the quaternion of that at that time. But if you remember, at the beginning of the demonstration, we started from this relationship here. One of the questions that we have raised during the lecture: what are the differences between this equation and the equation that we see at the end of the filter? So basically, the one related to these pk, the quaternion multiplication times the inverse of the quaternion. Well, just to clarify, the first part of the demonstration is only related to the propagation of the errors. So this means that this delta Q corresponds to the error associated to the quaternion between the reconstructed attitude and the real trajectory. So here is assumed that you know the real quaternion. So delta Q here is indeed the value that we want to know, and that is related to the uncertainty of our measurement. So the first batch of slides up to this demonstration here up to here are indeed important to determine these differential equations to determine the propagation of the errors. What we are going to do at the end, we want to also use, we want to determine the correction of the state. So we are going to multiply P, that is the vector reconstructed from the quaternion, to the predicted measurement of the filter. So delta Q here is indeed, as I said, the error associated to the filter. So what we want to do here is to determine these differential equations that are important to propagate the covariance matrix. So not only we want to determine the correction of our quaternion associated to the new measurement, but we want to bring the information that we collected from the previous observation to the next one. The only way to do that is to propagate our information, our a priori information. So one of the questions that I got during the weekend was related to this process noise Q that we have briefly introduced here. As I said, the process noise requires a dedicated lesson because, of course, is not, I mean, it is indeed a complicated topic that is related to the mismodeling of the equation. So when we want to propagate the covariance matrix that is associated to the uncertainty of the previous state, we know that we multiply by the transition matrix that is basically can be propagated through the matrix F that we have introduced here. So the matrix that give you the relationship between x dot and x. However, as I said, if you look at the appendix, you have an additional term that in that part is called the U. So it is an additional term to the differential equation that is not directly related to the state, but is related, for example, in this case, to the gyroscope error. So what we are going to do is that when we want to compute the covariance matrix, where we want to propagate the error, we don't need only the covariance matrix at the previous state, but we want to also propagate the error associated to the quaternion, to the gyroscopes. That's the reason why this represents a little bit much more complicated problem, because as you can imagine, you are not able to propagate the errors associated to the gyroscope by only using the transition matrix. But if you look at the appendix, what you have to do you have to multiply, so the transition matrix for that bit is indeed the integral of the transition matrix times the matrix B, that in our case is called the G. This part is not, of course, a part of the course, it's outside the scope of this course. So what I was suggesting is that if, in order to approach this problem in a simpler way, you can assume that it is indeed the error associated to the gyroscope. So you have an idea of what is the contribution of the gyroscope to the error of the quaternion. And in this particular definition, it is my reference to the tuning of the extended common filter. With the word tuning, is what I mean is that you're going to choose a value of this diagonal matrix that is consistent with the other matrix that is associated to the other source of error. The other source of error is associated to the Star-Traeger, for example. So usually the tuning of the filter is a combination, is basically a sort of comparison between your Q and your R. So if you want to have a correct estimation of Q, as I said, you should integrate using the integral of the transition matrix times G, this matrix here. But let's assume that it's too complicated. What you can do is that, you know, the error in the star trackers are, the error in the star trackers give you the knowledge that can be retrieved using only the gyroscope. So it is associated to the sigma k of the star trackers only. So when you compare here, your sigma k should be very close to your sigma tot that you have in your quest algorithm. Okay, so it is in the case that you only have star trackers. So this sigma here is associated to the instantaneous measurement of the attitude. So it could be star trackers, but it can also be some sensors, for example. Well, since usually RK is known because you know the accuracy of your attitude instrument, your attitude sensor, usually you can scale your Q in order to determine what is the actual scale factor or your actual accuracy of your gyroscopes compared to the star trackers, for example. One way to determine Q, for example, is that assuming that we're going to see later. So let's continue with the extended common filter. So let's assume that you have an initial estimate of Q, and you have also R because it's given by the error of the sensors. So what you have to do in this bit here, so in the extended common filter compared to the quest algorithm, is that your P0 will be indeed your Qk minus 1, k minus 1. So let's assume that our k is equal to 1, okay? However, this is not very useful, but we need to propagate this quaternion to this state here. So we're going to use the measurement from the gyroscope, omega, and so our quaternion equal to 1/2 of big omega times Q to determine our Q at a time k from k minus 1. This measurement corresponds to our prediction. As I said, at time k, or at time k equal to 1, t1, we have an additional measurement from the star trackers. So we need to combine the predicted measure of the quaternion at time q0 at the time 1. So we need to combine the two. We need our so-called innovation Z. Our Z is indeed the product, the quaternion product of pk times the inverse of the quaternion that was propagated from the previous epoch. This represents our innovation. However, it's still not our corrected quaternion. This only represents our innovation from our measurement, from our new measurement. So what we need to do, as you have done for the orbit determination software, you need to compute the normal matrices. So that is why I wrote on the top. From here, you will have the a priori matrix pk minus 1, pk minus 1. This one will be indeed this matrix here in the quest algorithm. So for example, at the initial time t0, you have this estimation of p. You need to propagate this one by using this equation. So by using the transition matrix and the process noise that we are still assuming that is known. So you have from one side propagate the quaternion, the other one the covariance matrix. By using this expression, you can indeed do the extended Kalman filter to determine your normal equations. It is a function of pk, so the pk minus 1, and r, so the error noise associated to the star triggers. Now we have everything to compute the correction in the quaternion. So what we want to indeed compute is our delta Q. But as I said, the extended Kalman filter also enables the estimation of the error associated with the gyroscope. So what you need to do is that once you have your innovation zk and your k, your normal equations, that is a function of the a priori matrix, you are able to determine the correction in the initial, so in your state that is given by a correction of the quaternion qk and the bias of the gyroscope that is equal to kk times the innovation. Okay, and so this is the end of the Kalman filter, because you have your estimated correction to the quaternion and to the bias of the gyroscope. You have also an estimation of the covariance matrix through this formula here. And you have also the update in the quaternion by indeed multiplying this correction here that you have computed to the a priori estimation to the predicted estimation that you propagated from the previous instant here, so this one here. So you have everything, and you can also indeed update your bias. So now, before going to the exercise that Paolo Capucci is going to present in a couple of minutes, I would like to so what you have at the hand is that your quest algorithm and the extended Kalman filter provides these different results. So as I said, so my example is only for the first instant. Of course, if you want to go to T2, you're not going to start from the covariance matrix of the quest algorithm, but you're going to start from the covariance matrix that was from the first, from this epoch of the extended Kalman filter. For the quest algorithm, every single instant is not, you don't have any relationship, so are completely decoupled. So what happened here is in that since you're not able to propagate the state, the a priori information, every single state in the quest algorithm is associated to the current noise of the star sensors. If you have the possibility to use the gyroscopes, so use the extended Kalman filter, you're able to propagate the previous information to the next one, and you're able to indeed reduce the noise of the measurement by including the propagation of the spin rate thanks to the gyroscope measurement. So the gyroscope have a very nice effect on your estimation if indeed your Q and R are well behaving. As I said, R is associated to the star triggers error, so is usually well known. The problem is find Q. So usually, so let's assume that you're assuming a Q that is very, very high. So you are weighting your gyroscope measurements. So it means that you're going to converge to something close to the quest algorithm. You're not using the information used for the quest algorithm, from the gyroscopes. But indeed, the extended Kalman filter has the possibility to correct the errors of the gyroscope. So you want to use that. So you have to find a value that is not inconsistent with R. So of course will be larger because you know that the accuracy of the gyroscope is larger. But you have to find a value that indeed enables a good convergence. So if you find a value that is a good compromise, so usually this is the tuning, so you try to iterate your errors in Q in order to see what is the best response in your filter. So this one, for example, represents a good response because you are able to reduce the error noise, although you see some mismodeling associated with the gyroscope. But usually the error is definitely lower compared to the Quest algorithm only. The other problem that you can have is that the Q is too low compared to R. So it's always larger, but probably is very close to R. What can happen is that you're going to have a completely divergence. So for example, you're going to see that your errors are going to converge to a biased solution. So the tuning is important. And as I said, if you want to face the problem correctly, you should propagate it by integrating the transition matrix times the matrix G. But if you want to do a rule of thumb estimation, you can, for example, try to scale Q in a certain way with respect to R to have the best response of your system. So with that, I would leave the floor to Paolo Cappuccio so he can share his screen and show you some example. And we can use the break for questions. So Paolo, if you want to share the screen, let me.
Yes.
Okay, let me.
You have to let me do it.
Yes, let me. Okay, stop sharing.
Okay.
Yes, go. You can go now.
So, I don't know if you see it.
Yes, yes, you're able to see.
Okay, so on the left we have, of course, the MATLAB code, and on the right I will keep the slides so we can do some comparison. I want to briefly introduce you the code because it's not that simple, so just to let you understand how it is organized. But I will just go into the details of the Quest and of the Kalman filter. So here at the beginning, we are loading the Hipparcos catalog that, of course, we need to construct our measurements from the star tracker. And here there are some other routines from SPICE, which is an extension of MATLAB developed by NASA, and it's useful to read the trajectory, kernel, attitude kernel, which is basically a file which contains the attitude of the spacecraft. So again, I will not give you details on this, but just to let you know that we are using actual data from Baby Colombo.
Yes, and you can also say that these files contains the attitude in terms of quaternions. So basically, we have a set of quaternions over time that give you, so these are a simulation because represents Baby Colombo that will orbit Mercury into 2025. So what Paolo has in his script is basically the prediction of what could be the attitude of the spacecraft at that time frame. So he's using a realistic Hipparcos catalog and the quaternion files that were simulated by the navigation team of ESA.
Yes, exactly. Actually, this is during the cruise phase because I changed the dates, but I mean, it's the same. It does not really change anything in the simulation. So just to let you know that this is based on actual estimation of the navigation team. And then here, what I'm setting is the length of time in which I want to simulate the attitude determination, and here step is how often I will use the star tracker data to correct the gyroscope data. So this is something that now I set to basically 10 Hertz. So I will update every 0.1 seconds. That, as you've seen on the slide, is one of the characteristic of the Star Tracker, which means 10 Hertz is a reasonable assumption. But we will see what happens if we will change this. And this is important because, as you studied for the Fahrenheit model, if this time is too big, so for example, is, I don't know, is, let's say, 1 hour, then the gyroscope will diverge, and so we cannot use those measurements. And then here we are building a time vector, so nothing really difficult. You should be able to do it. In this script, I can open it. We are building the nominal quaternion, as again said before, is based on the official data of Bepi Colombo. And what we do, we compute the trajectory. We have some trajectory of the spacecraft. We use also some other rotation, for example, to pass from the orbit frame to the body frame of Mercury, and so on. So again, this is details that I don't want to go into, but
yes, no, just to
let you understand that here we are building the nominal quaternion that we call Q true. So it's what Antonio called on the slide Q, without anything else on top. So is our objective, let's say, is to find this. We need this because we want to compute the star and read from the catalog. So here with then we go into the core of this exercise, and we launch this script, which is called SFAD, which stands for single frame at determination. In this case, we will just see the quest algorithm, but as you've seen on the slide, there are a few. But I mean, the concept behind it is always the same. So again, what we need to do is to compute the observable. So to obtain from the catalog and from the instruments the V and W vectors. So the vector of the stars in the optical bench frame and in the inertial frame. Again, I can open this quickly, but it's something that also will not be in the exercise. So what we do, we have built, we know the bore site of the instruments of the Star Tracker. In this case, we are using 3. Then I will show you how we can play with these inputs. But what we do, we compute the right ascension and the declination of the instrument, and then so the bore site of the instrument, and we can start to compute what we have in the visibility of each of these Star Tracker. Then with the script, we read the catalog, and we set a limit for now to 6 stars per 6 star per Star Tracker, with a field of view of 10 degrees.
So basically here is, so in the beginning of this subroutine, you are trying to, so the script computes the rotation matrix from the optical bench frame to the, actually from the sensor reference frame to the inertial reference frame.
Yeah, and then it builds the observables.
Because the problem is that the sensor itself as we have seen, so for example, a Star Tracker is on frame that is a little bit misaligned compared to the optical bench frame. So you need an additional rotation that basically give you that, right? So you need to locate the instrument with respect to the inertial reference frame. So what we are going to show here is definitely more complicated of what we are going to have in the homework. So this is a realistic scenario in which you have to take into account or possible error mismodeling. In the homework, of course, will be a reduced, so will be close to what you have seen. So will not be different, for example, you're not going to write different subroutines. So here is only to show you a realistic application of what we have seen before.
Yes, but I mean, it's also, yeah, there are a few more rotation, but at the end, just to let you understand, what we do with these scripts is to build the V and W vectors, because it's what, I mean, it's how we are simulating the readings from the star tracker. So it's the input for our quest algorithm. Just to clarify on this, but again, these are details that you don't really need to do during the homework, just to let you know how this works. But then going back in the single frame attitude determination code, what we are doing is for every star at every for every time step in which we have observables, what we do is we launch the quest algorithm. So this as input the V and W readings of the star generated before at a single time. So this just read the observables V and W obtained at the same time, which is what you have in the quest algorithm. Which sometimes is misleading. It's not something that, like in the order determination, that you accumulate observables with time, but here they have to be taken at the same time by the star trackers. So the number of observables will be much less than what you are used to with orbit determination. As you studied during the course, a star tracker can track a small number of stars, let's say less than 10. Here we're simulating 3, so we expect to get something around 20 stars. But then, going into the details of the code, what we are doing. First of all, we are building the vector A, which is the weight that we are giving to the, I'll go back to the slides, the weight that we are giving to the to a particular star, and we base this A on the error that we have in the catalog and in the reading of the instrument. We know that the sum of this A is equal to 1. So what we are doing is we are giving to to A the sigma of the catalog, then we divide by the sigma dot, which is built as the sum of this, so should be already normalized to 1, the sum of all of them, but I did it here again. So basically this is just to build the weights A that we have in the slides, especially in this matrix B. Then to build the matrix B, we are separating from the matrix of observable that was organized with 7 columns, but you don't really need to know these details. So we know the W and the V observables. What we have to do is to build the matrix B, which is the sum of A W multiplied by the transpose of V. And this is what we are doing in here. The Z matrix is something that is some slides after this. So our objective now is to build the matrix that we called K. Here, this is Z, and this is the matrix K. We want to build this because once we did it, we can solve the eigenvalue, the maximum eigenvalue, and find the quaternion. So we are still building the matrix K. Okay, so this is Z. B is, we already built B, and we know that S is the sum of B and B transpose. Z is the sigma, sorry, is the trace of B, And so we can finally build the matrix K. From this point, you could be able to solve this problem using several algorithms. Also, MATLAB have some of those, but generally they solve for all the 4 eigenvalues. So this is takes more cost, computational cost, which is something on the spacecraft we don't want to overload, because the computational capability on a spacecraft is less than what you can have, for example, also on your computer. So we have to use something that is efficient. One of the algorithms that we can use is the quest, as you studied. So we want to build this characteristic equation, which is basically the solution of this K matrix, this problem. If you do some computation, that I will try to show you the solution of this, we need to generate this matrix, which it's called adjunct or adjunct of S. And basically this is the definition. So we compute the inverse of S multiplied by the determinant. And then we have to apply the Newton-Raphson method. Alpha, which is this coefficient here, is the square of lambda minus the trace of p squared and the trace of this adjunct matrix of S. But this is something that, I mean, just comes out from the characteristic equation of K. You can compute by yourself. Something that is important is to define this vector x, x, which is not defined here in the slide, because we need to solve then for the, not for the eigenvalue, but for the eigenvector, which is the solution of our problem. Again, I will not read all of this, but this comes just from the mathematical problem of the characteristic equation. And after we set here 4 iterations, but actually already 2 or 3 could be enough. So it's not very difficult problem to solve.
So Paolo, just to let them know, so the reason why there is no an expression, because I got the questions by email about that expression of Q. Here we are showing that, so basically now you have the solution, but in principle the idea why, I mean, we didn't put in this slide is because I thought it was a good exercise to you to compute it. So now here from this MATLAB script you indeed have the solution, and you can have a direct comparison of what it is written here to what you have in that slide. Of course, in that particular case, as I said, it was assumed that lambda was equal to 1, because as you can see, you have that lambda is in the x expression. But anyway, so now you can also directly compare what you have computed with what it is written here. And so, Paolo, since we have 5 minutes before the break, I think that probably if you can go directly to the quest results, so we can start in the next the next lecture with the extended Kalman filter. And
okay, so I will launch the code. Actually, it will do all together. Here I have the results on this other screen. Okay, so what you see in here is basically for the time that I was simulating. So just it is 10 seconds because it is 100 steps with 0.1 of time separation. We have always 17 stars in the field of view with 3 star trackers. So we expect that if the stars have more or less all the same characteristics, so always the same accuracy, what we see here is that the uncertainty is always the same in time. And also on the other angles, we see the same characteristic. And again, as you can see here, the accuracy, also comparing with the slides, on the angle that we can retrieve is of a few arc seconds. As we will see later, this is not the case with the Kalman filter, because will be much better.
So just to so the angle CF5, right, are the so here it is assumed that the quaternion. So since it is a time integration of 0.1 seconds on turn Hertz in frequency, we are assuming that the quaternion errors are small. And so you're able to determine the angle of the optical bench frame over time, as we have seen before. So delta theta equal to twice the vector of the quaternions, right? So here the angle that you see is indeed assuming that approximation. So we are ignoring the scalar part of the quaternion, and we are assuming that the quaternion vector is directly related to angle variation, as we have seen in the slides. Okay.
Yeah, so basically we are assuming that the error is small, and so this is basically the representation of the vector components of the quaternion. So the first three components multiplied by 2. So this is what the Quest algorithm basically will provide you. If you are doing that is correctly. So basically the error is inside this uncertainty level, and basically all these, the important things to understand that all these measurements are independent from one another. So your estimation of the altitude relative to a time is completely independent from what happened in the past. So again, if you have a very fast rotation in this time interval, you will probably you will not able to say anything of what's happening in between. So you should have or some star tracker which will provide a higher rate of measurements, or you cannot do anything. I mean, you lose that information. Okay, so I don't know if we can go on, or it's we have to stop here.
I think that would be good for a break. So we can have 15 minutes of questions. And we restart by comparing the Quest algorithm to the extended Kalman filters. So.
Okay, so I'll go quickly on the Kalman. So as I said, I'll take also the slide so we can proceed in parallel. I see here. Okay, so just to I mean, introduce, I think, the most tricky part, which is the integration of these omega and psi, theta psi, sorry. So this theta, the EC stays for initial condition, and as we have seen here, it is taken as an high matrix, identity matrix, and the psi is taken as all zeros. So this will be useful just a bit later. Then here we just initialize our vectors and the bias beginning equal to 0, and just to give the start to the algorithm. Here we have the Q matrix, as Antonio said, and I will not give you more details on this. Since I know how I'm simulating the bias, I'm just taking those information to build also the Q matrix. But in general, if you know which instrument you have, and if the industry or whoever gave you the instrument gave you also an error model, you have to translate this in a Q matrix, which takes into account basically the error of your instrument, as you will do, for example, for the star tracker. It's just a different shape, let's say. If we have time, we will see this later. Then what we have to do is to apply at every time the extended Kalman filter. And this from the slides should be, a bit more clear from today. So what we have our predicted measurements that it's basically our propagation of the Q that we estimated at the previous step, which is an input of the algorithm, which is what we computed with the quest. And then through the transition matrix, we can propagate this in time. To compute and to integrate the transition matrix, we have for the C part basically just the product of what we have seen in the previous slide in here. So is a multiplication of I call the matrix omega for this mat theta, which is just the psi at the previous step, minus the 1/2 of the identity matrix. So applying this with the other function that you already know from previous exercise, you integrate this equation. It's very straightforward. I think that is more complex to see on the slides than doing directly. So once you have the initial condition and the derivative, basically you have just to integrate this. And the same we can see for theta. So the important things that you remember is the initial condition and the derivative. So then it's just as you did with the previous exercise, the transition matrix. The expression for theta, again, we start from the rotation matrix that in this case I just put in a matrix form for the product. And then I multiply for, again, I call this always the same, which is mat theta, but it's just the value of omega at the previous step. Okay, so the rotation of the spacecraft for this omega term. And then this is computed automatically by the integrator in MATLAB, and what you get at the end is this matrix that we call this theta all capital, as you saw on the slide. For same for theta, for psi, sorry, and then we can build this phi matrix, the transition matrix, which has theta and psi basically in the first row, and then zeros and identity matrix in the second row. So this, I guess, is the most difficult part, because then you have just to integrate the quaternion to the next step with the equation that you already know. So once you know omega, you know everything. So we'll just very quickly, and then going into the actual Kalman filter. We have to initialize our code, so initialize our quaternion. So we are doing the product. Here, this is a function that it's in we built in MATLAB, but I mean it's not in the normal package of the code. So you have to write it. But I mean, as you see, is also in the slide. This is shown how to do it, and then we build. Yes,
the slide this is the multiplication of to quaternion. You should use the same formulation that I show you. So the one with the cross into the circle. If you use that one, that would be it.
So maybe this was a bit confusing, but here in this step of code, Y is just what we called on the slide Z. So it's the innovation.
We got a question regarding the code. The code, of course, was not uploaded on the website, because if you upload the code, you will be able to do the.
Then it's finished. The exercise is finished. But I mean, maybe I cannot tell, but I think this is recorded, this lecture. So
yes, you have plenty of time to stop. I mean, he is going maybe too fast for you now to gather all the information that you need. But if you rewatch it, I mean, you can stop by each part of the code. Basically, you have all the information. But of course, we are not able to give you the code, because otherwise
no.
it would be...
No, but I mean, also this is a bit more difficult than what they should do then. So I'm just also skipping some parts, so otherwise becomes more confusing, I guess. But again, here you really see straightforwardly what we have on the slide. So we are building this innovation vector, multiplying the two quaternions. Then the H matrix, as you can see in here and on the slides, this is the identity matrix and zeros. And then we are building our Kalman gain. I've obtained it is the propagated covariance matrix multiplied by H, as you can see in this expression. What I think is important to underline is how we compute the delta X, which is this Kalman multiplied by innovation. And this innovation depends only on the quaternion and is not related in any way to the bias or to the omega. Because also, as you can see from the slide, this is computed just as a product between quaternions. So this K is actually not a square matrix, because what we want to obtain is a delta X which takes into account the quaternion and the bias, but is multiplied only for a quaternion. So basically, if this is a 4 by 1 and we want as output a 7 by 1, we need this to be a 7 by 4. Okay? So this is something that I mean, you can use as a check, but I don't know if this is so straightforward. Then once you do this, actually, then what you should do is very easy, because you know from this delta X, which is the part related to the quaternion, which is the part related to the bias. You can this way actually update your quaternion doing this product, as you see from the slide, and basically iterate the process to the next instant in time, to the next time step. And here is the innovation of the covariance matrix, which here is called tilde, I mean, but it does not really change anything. Again, something that you should take into account is that if you are passing from the quaternion problem to the angle problem, remember and pay attention on how you rewrite these equations. Because at that point, as I said here, for example, it was a 7 by 4, but actually it will be a 6 by 4. Actually, no, sorry, a 6 by 3, because then your delta will be 3 angles and 3 bias. So also depends on which problem you are going to solve, if you want to do with the quaternion or with angles. Then on this, I think we can just go with the example without spend too much time on this. If it's clear or if they have question, I don't know, because I think that the most tricky part is to initialize the code. But when these terms are clear, I think it's very straightforward.
Scusi, una sola domanda.
Yes?
Prego.
Quando facciamo l'integrazione per trovare la matrice di transizione, ogni volta come stato iniziale usiamo quello del passo precedente, tranne al primo che usiamo la matrice di identità?
Just to translate the question, at every time step, are we going to start from the for the integration of the state transition matrix from the previous step, or we start at every time step from the identity matrix and zero matrix? So, as I said, this is basically the integration at the same time step, okay? And we are passing in input always the initial condition of theta and psi. So you are actually starting every time from the identity matrix and zero. But why this? Because you are updating the state at every time step. So at every time step, your state transition matrix at zero basically should be an identity to itself. I try to explain better. When you go from T0 to T1, you need the state transition matrix. But then when you arrive to T1, that is your, now is your nominal and initial state to reintegrate. And so your state transition matrix basically should be an identity. So it represents the state T1 at time T1. I don't know if it is clear.
Sì, grazie.
Okay? Because you are updating the state. Okay?
So there is a question regarding the definition of the matrix R. Probably here you can show the code, because it is indeed easier here to understand what the matrix are. So the matrix R is the, go ahead, sorry.
Sorry. The matrix R basically contains just the measurement error that we computed through the quest algorithm, basically, and so depends on the catalog and the star sensor itself. So here, now let's try to find it, but
so in the code previously is the sigma that you use for the quest algorithm to compute the coefficient A, right? So when you compute the coefficient A, you scale that sigma that you have in the diagonal matrix here to the sigma thought that was in the formulation of the covariance matrix. So here you have that for each measurement, for each star, let's say, you have an associated sigma that is related to the star catalog, so a delta in V, and an error in delta W that is an error in the sensor, for example, a misinterpretation of pixels or a magnitude error, as we have seen during the course. But you can show you in the code, that would be clear.
So here we are passing as initial, as an input, the matrix R. But where we define this, I mean, this is in this matrix R is actually defined in the main script in here. Here. So actually we were using this RK. So this RK is basically the output of the quest algorithm. So for every vector, it is basically the output of the PQQ matrix that we saw before. Okay. So it's the covariance associated with your vector PK, which is the output of the quest algorithm. Okay. So the matrix R should come out from here.
That is, it is related, as you can see in the slide, from the two errors of, because the covariance matrix from the quest algorithm is only associated to the star sensors, if you have star sensor, or to the other sensors that you are including in that single frame determination. So if you can show now the result, that would be
yeah. Okay, so just to go quickly on this, I think we have to explain the other sensor later. So again, we are reobtaining the triangle. This is always expressed in the angles. And the number of stars, okay. And as I showed before, is always 17 stars. Okay, now the extended Kalman filter is running. It takes some seconds, it should not take long. And also, as you can see, the quest algorithm is actually performing much faster because it does not need to integrate anything, but it's just basically solving an equation with a Newton-Raphson method. Now, the extended Kalman filter has finished, so I will try to put these two related. So what you can see is how the quaternion, the covariance on this angle is decreasing with time. And actually, something that from the slide was not very visible because it was that was integrated for a longer period. But basically, we start from almost the same value as the quest, and then it reduces in time thanks to the contribution of the gyroscopes. And again, both the covariance and the error are lower. Here we can zoom to find to get an idea. So this is around 0.5 arc seconds, while here is almost to 1.5, 1.6. Of course, now this is just an example, but if you propagate this for a longer time, it can also be increased by an order of magnitude the accuracy using the extended Kalman filter. And another things that we can show is
can I say just something more here? Because I mean, here, for example, is really clear the tuning of the filter. So let me note something here. So yeah, you can, yeah, perfect. So if you zoom out, here probably it is easier to explain what we mean with a perfect tuning or in a good tuning of a filter. As you can see here, the inclusion of the gyroscope measurements leads to a perfect convergence of the attitude error to 0. So we are tuning the filter correctly. That means that the metrics R and the metrics Q are indeed retrieved correctly. I don't know if we are able to do a test by changing these two metrics easily, but probably we can try, for example, by multiplying Q for a scale factor. What you can see here, that could be a good test to do, but let's see if we can do. So what Paolo showed you in his software is that Q and R are perfectly tuned because R is assumed to be the covariance matrix, the one that we call the PQ from the previous steps K-1 from the quest algorithm. So give you the information of the covariance matrix associated to the star, sun sensors, or whatever you're using for the single frame determination. The other thing that he show you is that the Q is also assumed correctly. So he integrated that by assuming the matrix gamma that is in the process noise appendix. Gamma, as I said, is the integral over time of the transition matrix that we have also seen times G, that depends, that is the matrix that multiply the effect of the gyroscopes over time. So by including these two terms correctly, of course, you have a perfect tuning of the filter. You can test that probably you are not able to do that correctly, because I mean, that one is straightforward, of course. You have the knowledge of R from the PQQ. It's a little bit more complicated, determine gamma. So what you can do, for example, try to attempt certain values of Q. What you're going to see if you try to determine Q with a different approach is that the tuning of the filter is going to provide you or different convergence if Q is too tight, so it's too close to R. If it is too small, if it is too large, you're going to see larger oscillation of the signal, and probably you're not always able to converge, as you can see in the slides. So what you're going to see here is indeed, if you tune the filter correctly, that's what you get. And so this is the perfect way to tune the filter, and what is done in basically in reality. Okay, so I don't know, Paolo, if you are able to rerun that by, for example, multiplying Q by a scale factor, for example, 1000, just to see if we're, for example, you are reconverging to the, so you should, probably Q was, yes, in the previous one here. If you multiply Q by 1000, let's say, probably it's too large, but let's try it. You should see that probably what you're going to see is that the effect of the quaternion of the gyroscopes is basically negligible, because you are weighting the effect of the gyroscope. So let's see what he says.
Let's see what happens.
Yes. And so you were saying something else in the meantime, I think.
No, I think that was it. I mean, it's just that basically the real advantage is not only that you know that with a better accuracy, but knowing the rotation, you can only know what's happening in between.
Yeah. Yes, indeed. And the other thing is that, for example, it is difficult to do.
Actually, it's not changing much.
It's not, maybe 1000 is too small. Probably we need to. Oh, but that Q is the one that is afterwards integrated. So probably is more complicated than that.
Yeah,
so
I mean,
should,
and also for now it's very small, because as I remember, this value are something 10 to the minus 15. So
yes, because the main error is given by the propagation of the error. So probably in order to do something correctly, no, it probably what you, yeah, you can try that, but probably that could be a useful and interesting result that you can show you in the homework if you're going to do this, the Kalman filter, is that if you fix the Q without propagating it, so by using a fixed value of Q, you're going, probably you can see that this effect even larger, because probably here what happens if you is that the Q is the initial error associated with the gyroscopes, but the main error is given by the matrix gamma, so the propagation of the errors that indeed induce to a larger effect. To the larger effect of the gyroscope in the. So let's see what happens here, but
I mean, it starts to have a shape that you were commenting before.
yeah, because I mean, as I said, it is you have to
start to
yes,
it. So it's not that easy to understand, I mean, which is the value, because now, for example, for the gyroscope, we assumed very good performances.
Yes.
So we should degrade it maybe even more, but you start to see that it's oscillating and it's not going to zero as before.
Yes, you have this oscillation given by the fact you are not tuning correctly the filter. So Paolo, I would thank you for this one and this exercise that I think is really interesting. If you have any question to the exercise, you can email him directly.
Yeah, I have the university mail as Antonio, so paolo.cappuccio@uniroma1.it.
And so, as I said, that probably the homework will be on the attitude determination, and you have to solve for the quest algorithm, and you will also have an optional, I don't know if it is optional or not, let's see, but an extended common filter exercise as well. So I would conclude these 50 minutes with the earth sensors. So let's see how this final test works. But as I said, tomorrow we're going to conclude the part of the attitude determination, so including these sun sensors, and we need to conclude in the last couple of weeks for the control theory. So now that we're able to determine the attitude, we need to control the satellite, and that will be the main focus of the next couple of lectures.
Stop sharing, okay?
Oh yeah, so okay, thanks. So I will start this part, and thanks, Paolo. So one question was regarding the homework. The homework will be probably the second week of May, but I mean, we are flexible on that. So if you think indeed that you need you have a week in which you don't have other duties, probably you can do also the following week. So for example, May 20, but approximately May 14, May 15 would be the date. Okay, so let's conclude this lecture today by reintroduce briefly the Earth horizon sensors. So what we have seen so far is the extended common filter, that it is the software that we need to determine the attitude using sensors that give you the single frame determination and the gyroscope that give you the propagation of the errors. The Earth horizon sensors will be dealt in this lecture by not basically using the sensor for in quest algorithm or in extended common filter, but in principle you can use the Earth horizon sensors to determine the attitude of the spacecraft, or especially two axes of the attitude of the spacecraft. So what we are going to see, that you can apply a method for Earth horizon sensors that give you a good knowledge of the spacecraft for the roll and the pitch axis. So that's the reason why probably you don't need an extended common filter or a quest algorithm, because basically what you need to do is to use the Earth sensor in order to determine the orbital frame, so your body frames with respect to the orbital frame of the spacecraft. So usually the case that you have is indeed a satellite that is orbiting the Earth, and you need to determine, for example, to keep the nadir pointing of the spacecraft. So you have that your x direction of the spacecraft of the body corresponds to the x direction roll axis of the spacecraft. The y axis, the body frame of the spacecraft, corresponds to the pitch axis of the spacecraft. And you have the yaw axis that indeed is basically the axis that is close to the z-axis of the body. So you need to have an Earth body and Earth horizon sensors in order to determine the attitude precisely in this direction and this direction. Of course, you're not able to provide any information on this orthogonal direction because you have an ambiguity that is related to the sensor itself. We have seen indeed that the Earth sensor is given by a scanner that basically is try to measure the flux of the Earth by scanning a certain field of view of the instrument. once this scanning system, the scan cone is intersecting the Earth, you're able to detect a signal here. And since it is indeed reorienting, let me see there. So when the sensor is not indeed looking at the Earth, you're going to lose the signal here, and so you have two measurements, delta 2 and delta 1. Delta 2 and delta 1 give you this energy, that this intensity that you're getting from the sensors is related to the roll axis variation, because since this is the Earth disk that you are going to see from the spacecraft. So if you're looking the spacecraft from above, you're going to see the Earth as this disk here. So basically, the scan is indeed going to intersect the Earth disk here and losing the signal here. So the magnitude, so this intersection here give you the it is directly related to the phi angle. So the roll angle is directly the delta 2 minus delta 1 divided by C1 minus E0, where E0 is also the term is directly related to the altitude of the spacecraft, because the shape of the Earth disk depends on the altitude at which the spacecraft is on its orbit. So if you want to have, if you want to determine the intensity, so the roll axis of the spacecraft, you need to know the altitude at which the spacecraft is. The other angle that you can determine is the pitch axis using the Earth horizon sensor. So the Earth horizon sensor give you a good pitch angle estimation if you include a vertical reference to the sensor itself. Because if the spacecraft is rotating along this axis, also this vertical axis is going to rotate. And so what you're going to see is that in your detector, the intersection of the vertical axis is going to change in this signal that you have from the sensors. So if you are, for example, that the vertical axis is exactly in the middle, that means that you have a 0 pitch angle, for example. But if you start to have a misalignment or a misorientation or a different orientation of the spacecraft, you're going to detect a signal that is governed by the sum of delta 2 plus delta 1. You have a sum here because the delta 2 and delta 1 are computed with respect to the vertical axis. So this one is positive and this one is negative. The other coefficients are also dependent on the sensor itself, so are properties, optical properties of the sensors. So from here you can understand that if you know the altitude of the spacecraft, by using one Earth horizon sensor, you are able to determine the altitude of the spacecraft in the single reference frame for the roll and pitch axis. However, you need to know the altitude, and so this instrument alone cannot provide, indeed, a good knowledge of the altitude by itself. One question that I got last Thursday was regarding why we don't include another sensor here that is going to point to the roll axis. So we are able to determine uniquely the pitch and roll axis by using two different sensors. Well, this is the main problem for this solution is that you are not able to include many sensors that you want. In space, as you know, you want always to reduce the number of electronics, number of sensors, because you want to reduce masses and powers consumption. So that will not be a good solution. And on top of that, that will not give you a solution for the altitude. So you still need to know the altitude of the spacecraft. A solution that addresses these main tasks is the Earth sensor that is called the dual scan sensor. So it is a sensor, so you can, in principle, use two different sensors that are pointing at two opposite directions. So basically, you're going to have a scanning of this region of the Earth disk and another scanning here. If you have both, you are able to determine the altitude of the spacecraft on top of the roll and pitch axis. So you are including basically other two observations, because if you have only one Earth sensor here, you have two measurements here. They give you information on the Y, so on the roll and pitch axis. But you have an ambiguity because so basically this response depends on where the spacecraft is. If you include another sensor here, you're able to include the other two measurements, so 3 and 4, that give you a larger amount of measurements that you are able to use to determine the altitude of the spacecraft. So the main problem here is that you're including other two measurements in order to improve the altitude of the spacecraft. So you can use two different Earth sensors to determine roll and pitch axis without any ambiguity related to the altitude of the spacecraft. However, as I said, you always want to avoid any possible errors induced by any possible error or any possible I mean, you don't want to, you want to avoid multiple instruments on your spacecraft. So you want to minimize the number of instruments in your spacecraft payload or your spacecraft instrumentation deck. So one solution, for example, could be to use the same Earth horizon sensors with dual scanning mirrors. So basically, the same sensor can use two different mirrors with a movable scan part that is going to look at two different portions of the Earth. So basically, with one instrument, you are able to do what was in principle suggested with these dual Earth sensor configurations. So these configurations, this dual scan configuration, you can see you will have this scanning of the Earth disk and a second scan, because you are able to have this rotating mirror that is going to illuminate one mirror and the other one by looking at different regions of the Earth. So the main problem, and what we are going to conclude today, is indeed that we find a configuration of the instrument. So this is the bolometer, this is the sensor, so this is the lens that focus the dual scanning of the instruments to the sensor itself, that enables one instrument to do the what two Earth sensors can do in principle. So we have to be careful then that there are also disadvantages to this configuration. First of all, there is angular rate is more limited. So you have that you are not able to look at two separate regions of the Earth, but you're going to use regions that are not separate, largely separate from the two scanning. And the other thing is that, as I said, you need to use additional sensors in order to have a 3D determination of the spacecraft attitude, because the Earth sensor is only able to give you an information on the pitch and roll axis. So you need an additional sensor in order to determine the attitude of the spacecraft. For example, in conjunction to Earth sensor are used the sun sensors, or, for example, star trackers. And you have also to be careful that the sun, for example, can be a problem for Earth sensors. And the use of a dual scan Earth sensor is indeed useful, because you are looking at 4 different points of the Earth. So if you have the sun, for example, is in this direction, the detection of this point will be not possible, because basically the sunlight is going to saturate this horizon limb. So by using a dual scan sensor or 2 different Earth sensors enables to have 3 different measurements that are indeed enough to determine the attitude of the spacecraft for the roll and pitch axis. So tomorrow we're going to see what is the method that we're going to use for Earth sensors, because, as I said, since Earth sensors already are not able to give you information on the 3D of the spacecraft attitude, we can use a method that give you direct information on the roll and pitch axis by using the Earth horizon sensor readout. The other important thing that you have to take into account is that these horizon sensors have many important characteristics that we have to take into account tomorrow. So tomorrow we're going to conclude this part and the sun sensors, and we will start to introduce we are going to introduce the control theory. So I will pause the recording